right, so last week we learned how to graph sine and cosine, okay, and they were what we call sinusoidal curves, so the wave functions, okay. Now we're going to learn how to graph tangent, cotangent, secant, and cosecant, and none of these are going to be sinusoidal curves, okay, they're going to be strange. So we're going to talk about how to graph each of these things. So if you remember, a tangent of our angle is always going to be sine of the angle divided by cosine of the angle. So t represents theta or whatever you want, x, doesn't matter. All right, so if I have a unit circle and I'm at 0 radians, then the sine of that is going to be 0 and the cosine is going to be 1, right? Because it's the point 0, 1 over there. All right, 1, 0. All right, so the tangent then is going to be sine divided by cosine, which is 0 over 1 or 0. But if we're at pi over 6, remember the sine is going to be 1/2, the cosine is going to be root 3 over 2. So when I divide those out, it gets a little bit messy. We've done this before, though, and it will simplify to root 3 over 3. And then pi over 4, if I divide it out, I have root 2 over 2 and root 2 over 2. So if I take sine divided by cosine, I get 1. Pi over 3 is going to give me root 3 over 2 and 1/2. So when I divide those out, I get root 3. And pi over 2, that's the point up here, which is 0, 1. So it's going to be 1 divided by 0. So what happens when I do 1 over 0? Undefined. Undefined, exactly. So that is going to be what's most important about a tangent function. A tangent function has places where we have undefined. Okay, in other words, it has vertical asymptotes. So we're going to have vertical asymptotes for these. So let's say tangent is undefined at x equals pi over 2, but where else would it be undefined? Where else would I have a sine value, or not a sine value, a cosine value of 0? Because I'm doing sine divided by cosine. 3 pi over 2, negative pi over 2, and so on. So what we wrote last time is we said pi over 2 plus pi k. Do you guys remember doing that? So if I keep adding pi or subtracting pi from pi over 2, I'll get all those different answers. So we say where k is an integer. So if I'm drawing tangent, I want to start with the places where it's undefined. So it's undefined at pi over 2 and negative pi over 2. So what I'm going to do is I'm going to draw vertical lines that are dotted, right? Vertical asymptotes. And then it's going to be every pi after that. So it's going to be 3 pi over 2, 5 pi over 2, and so on. And I could go this way.
Wait, is that pi over?
It's negative pi over 2 and positive pi over 2 today. Make it look a little cleaner for you. If you remember, tangent has a period of pi. We've talked about that before. A period is like when it's repeating, right? So on our unit circle, the tangent is equal to 1 at pi over 4, but then also again at 5 pi over 4, right? So it's every like half rotation around the unit circle. All right. So let's talk about some of these. So we said that at 0, our tangent was 0. So we're starting at 0, 0. Then we said at pi over 4, the tangent value was 1. What about a negative pi over 4? What do you guys think? Yeah, it's negative 1. Okay, and you can find other values. You know, we said pi over 6 was root 3 over 3. Well, if you find what root 3 over 3 is a decimal, I'll go ahead and do it. What is root 3 over 3 as a decimal? You're speedy. Can you do it for me? So it's 0.577. So it's a little bit more than 1/2. All right, so you can graph all these different things that we've done, but what's going to happen is it's going to end up looking like the x cubed function. It'll look like this. That's kind of strange. And let's say we put our calculator in degree mode. That's a way that I think most people understand. Go ahead and put it in degree mode really quickly. All right, what if I did tangent of, what's a degree that's close to pi over 2?
30.
No, pi over 2 is 90. So I want to get closer and closer to pi over 2. So let's try like tangent of 89 in degrees. When I do tangent of 89 degrees, I get 57.28. So it's shooting up really fast. But what if I do tangent of 89.99999. Let's do 5 nines after there. I get 572,9577.951. So I get over 5 million. Okay, so do you guys see the closer you're getting to 90 degrees, this is going up to infinity. Do you guys get it? And same idea, if you did negative 89.9999, right, it's going to go down to negative. Okay, that's why it's doing that little shape there. Okay, and it repeats. So it repeats every pi. So you're going to keep having the same shape, this like x cubed type shape, over and over and over. That's what tangent looks like. Strange, isn't it? So it's not like the wave that we had before for sine and cosine. It's a little bit different. There's asymptotes. Okay, does that make sense? All right, so it says, what is the domain of tangent then? So there were certain things that we couldn't have for t, right? If we plugged in certain things for t, we got undefined. What were those things?
Pi over 2, 3 pi over 2.
Exactly.
Pi over 3.
So pi over 2 plus pi k, we write it. So x can't be those values. X is not allowed to be pi over 2. It can't be 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So we usually write where k is an integer, remember? I told you if you didn't do that on your homework, I would understand what k is. You don't have to write where k is an integer every time. All right, what is the range of the tangent function? So what are all the y values we get out? We actually get out everything. So this is all real numbers. And what is the period? So the period of tangent is pi, and we've talked about that on the unit circle as well. So tangent of t is equal to tangent of t plus pi. You could write it that way. So every time you add pi to your angle or subtract pi from your angle, you get the same thing. You can even say t plus pi k if you want, every integer multiple of pi. All right, so state all values of t for which tangent of t is 1. So we've done this before. So what you could do is you could, graph tangent on your calculator, and you could graph y equals 1 on your calculator, and then you would find all the places where it's crossing. Well, that seems a little crazy. So we're not going to do that. So instead, we're going to think back to our unit circle, because I tell you guys that for a reason. It's really the easiest way to find these quickly, right? So if I have tangent of some angle equals 1, that means sine over cosine is equal to 1. So sine is equal to cosine. So sine, the y value, equals the x value in 2 locations. Right? So t would equal pi over 4, but you'd also have 5 pi over 4 and 9 pi over 4 and all those different things. So what we write is pi over 4 plus pi k. Do you guys see why the period is pi for tangent now? So that's where our sine's everything in like the first quadrant and third quadrant, second quadrant, fourth quadrant, and so on. All right, so here's what you guys will have for your homework. You're going to have to sketch things like this, okay? So it says roughly sketch a graph of h of t equals tangent of 1/3 t plus pi over 6. Okay, and what we notice here, minus pi over 6. So what I notice here is that I have 2 horizontal transformations. Do you guys remember what we do if we have 2 horizontal transformations? No. Yeah, we have to factor. So we rewrite. And we rewrite by pulling that number in front of t out of the parentheses. Okay, so I have tangent of 1/3, and then I'm going to have t minus something. So let's think. 1/3 times something is going to give me pi over 6. Yeah, exactly. I need pi over 2. Do you guys get it? How it works? So if I'm listing my transformations, I know that I'm going right pi over 2. Okay, in Precalculus, you have a word for that. We call that the phase shift. All right, and then from there, I'm going to have some kind of horizontal stretch or compression. What do you guys think? If I have a 1/3 here, what do you think it's doing?
Compression of
a stretch, right? It's going to be a stretch. So it's going to be a horizontal stretch. Yeah, it's a horizontal stretch because it's inside parentheses. It's in with the x value or t value in this case, right? Now, what you guys could do, and you guys did this with sine and cosine, is I had you guys remember on sine and cosine that the period was equal to 2 pi over b. Now, that's not what it's equal to for tangent because our period is not usually 2 pi. What's the period for tangent? Pi. So it ends up being pi divided by b. So if our b value is 1/3, right, then when we plug in 1/3, we get pi divided by 1/3, which is pi times 3/1. So we do get 3 pi. Do you guys see how that works? So if you just memorize that formula, you can get it. But it's really, I think it's best to just think of your transformations. If you guys are solid on your transformations, what we've been doing all year, and we did last year too, like you'll be fine with this. So what this changed was the period, right? A horizontal stretch is always changing the period. So our new period is going to be 3 pi. Okay, but otherwise it looks just like tangent. So tangent, if you remember, it had our starting locations at, so looking back here, our starting locations at pi, well, our vertical asymptotes, I guess I should say, are pi over 2 and negative pi over 2. Okay, and our starting point was 0, 0. Okay, where's our starting point going to be now? Instead of 0, 0, we're going to go where? Yeah, we're shifting to the right, pi over 2. Do you guys see it? So we're going to be over here at pi over 2. And that's going to be where our cubic function, like I call it a cubic function. It's not really a cubic function. It looks like x cubed, right? Where that little like turn is going to be. Okay. But we want the whole distance to the left and the right. I want to go out 3 pi total. So I want this whole thing to be 3 pi. Do you guys see? So think about where I would be. What's the right asymptote going to be? It's half of 3 pi. 3 pi over 2, or 1.5 pi, right? So if I start at pi over 2 and I go to the right by 3 pi over 2, let me write that in. So I'm adding 3 pi over 2. Yeah, I'm going to be at 4 pi over 2, which is 2 pi. So that first asymptote is going to be at 2 pi. What about the other one? Yeah, if I subtract 3 pi over 2, negative, not 2 pi, just pi, right? I know, because we started at pi over 2, we didn't start in the center. All right, and then from there, it's looking just like tangent, except it's just wider, right? Because the period's bigger. The period's 3 pi. So it's just going to look like this. So just kind of stretch it out. So what if I wanted to draw more than one period? So sometimes on your homework I'll say include at least 2 full periods or include at least 3 full periods. That means that at 2 pi, if I go to the right 3 pi from that, I'm going to be at 5 pi. And directly in the middle is going to be where I have my little turn. What is that point that's directly in the middle? I didn't draw that very well. What is it? 3 pi over? Nope, not 3 pi over something. Dang, I cannot draw this. I want to draw it the same as the other one, but it's really hard with tangent. Yeah, I'm going to add 1/2 pi, so I have 3½ pi, which is 7 pi over 2. Right, and then same thing over here. So if you wanted to draw one over here, you subtract 3 pi, so you're at negative 4 pi. So if I go back 1½ pi, I'm at negative 5 pi over 2. Okay, oh, fractions, your favorite. Yep. All right, good. All right, next up. So we talked about this before. So trig functions are called odd or even based on their symmetry. So a function is what we call even if I plug in a positive x value and a negative x value and I get the same y value. So the thing I want you to always think of is y equals x squared. If I plug in a 2, I get 4. If I plug in negative 2, I get 4 as well. Does that make sense? So I get the same value. So if I fold across an axis, which axis is it symmetric across? The y-axis, right? So our answer is going to be symmetric across the y-axis. All right, this one I wrote wrong. I should have an f of negative x somewhere. So this f of x, let's make this f of negative x. So if I plug in a negative x value and a positive x value, I get the opposite. I get opposite y values. So if you think of y cubed. If I plug in 2 and I plug in negative 2, 2 comma 8 and 2 comma negative 8. Does that make sense? So this one is not symmetric across the x or the y-axis. It's like you have to do like both at the same time. So what we call this is symmetric across the origin. So really what happens, so kind of look up here, do you guys see my picture? Is it like rotates around? If you rotate it 180 degrees, you get the same graph.
So it's just
Does that make sense?
X.
It's what?
X would do the same.
Y equals x does the same thing, yeah. This is odd. It has an odd power, that's usually how you can tell it's odd, right? But sometimes things are neither. Like I was just saying to Kyle, like if something has an odd power, then it's going to be an odd function. But what if you had a combination? If I had x cubed plus x squared, that's neither. It's not going to be odd or even. Okay. So what we call this is symmetric across the origin. So odd is symmetric across the origin, which means that you can rotate 180 degrees and get the same thing. So sine, do we think it's odd, even, or neither? Can I rotate it? If you turn your paper around, literally, what do you get? Same thing? Yep. Cosine? Even, yep. If I plug in pi over 4 and negative pi over 4, I get the same thing. What about tangent? Odd. One thing I did notice, I took this picture from somewhere, but the range, it bothers me. The range should have brackets on it. So the tangent one's fine, but it should be -1 to 1 with brackets on those. All right. So let's try cosecant. So cosecant's different than tangent. We're not doing cotangent, we're doing cosecant. And cosecant is the reciprocal of sine. So whenever you have one of these reciprocal ones, so cosecant or secant, you need to draw its reciprocal first. This is why this homework assignment, I would probably use some colored pencils or highlighters or something like that, because you're going to have to draw a lot of intermediate steps before you have your final answer. It's kind of annoying. Okay? So I'm going to graph the graph of sine first. So let's make this 1 and this -1. Do you all remember how to graph sine? You should always know how to graph sine and cosine. If you don't know how to do those quickly, you're going to waste so much time on your test that you're going to run out of time. Okay, you need to know how to do those. So sine starts at 0, 0. And its period is 2 pi, meaning it's going to be back at 2 pi, or back at 0 when it gets to 2 pi. And it's going to go up, down, and then back up. Okay? So it's crossing at pi. It's at its highest point at pi over 2 and lowest point at 3 pi over 2. So it's going to go up, down, and back around. Are some of you guys pretty good at drawing this? Many people just kind of do like points. It's curvy. It's not just straight lines like connect the dots in kindergarten. Curvy. All right, and then same thing over here. So it's going to go down and then back up. And you can always use your unit circle if you were confused on some of these values. Remember, you could find the sine of pi over 2 and say, oh, the sine of pi over 2 should be 1. So it should have pi over 2 comma 1. All right, so that's sine. Okay. Cosecant is the reciprocal of sine. So what about 1 over 0? What's 1 over 0? Yeah, it's undefined. Everywhere where sine crossed the x-axis, right, where sine was equal to 0, that's actually going to be an asymptote for cosecant. So we're going to have an asymptote here, here, here. Do you guys see where I'm crossing? Everywhere it crossed the axis, that's where we have an asymptote. Here and here. All right. Now from here, it's super easy to draw, but I'm going to kind of explain why we draw it this way, and then maybe with secant, you'll be like, oh, I totally get this, because we're going to do another one, okay? So if I take the reciprocal of 1, 1 over 1 is 1. So at 1, I'm actually at the same point. And same with -1, I'm still at -1. So most people are like, oh, it's going to be exactly the same as sine, but it's not, okay? Let's think about this point right, well, not right there. Let's do it a little bit lower. Right here. What's the height of that point? Can you tell on my graph? 1/2. What is the reciprocal of 1/2? 2. So that means on cosecant, I need to be at a height of 2 there. And same thing over here. Make sense? But what about as I get closer to the axis? What if I'm moving, you know, like right here? So I'm at, let's say I'm at a height of 0.01. What's 1 over 0.01? You can do it on your calculator if you need to. It's 100, right? So that means as I get closer to the x value, I'm going way up high, way up to 100 and further. So it bumps up the other direction. Do you guys see it? So originally we had a curve that went downwards. Now we have a curve that goes upwards away from it. But the touch is on the 1, on the height of 1. Do you guys get it? Every single bump that you have on your original, on your sine, is going to go the opposite way for cosecant because of the reciprocal thing. So this next one, if I'm at a height of -1, I'm going to go away from that height of -1. I'm going to bump away. I'm never going to cross those 2 bumps. Do you guys see what I'm talking about? It's really hard to explain using very technical terms, bumps. So same thing here. I'm going away from the bump and away from the bump. So do you guys see what cosecant looks like?
So it's just parabola.
It looks like parabolas, yeah. So basically it's going to be like you will have asymptotes. And the first one's going to be a bump here. The second one's going to be a bump here, and so on. So they're going to alternate the direction that they go. But the lowest that they go is 1, or I shouldn't say the lowest. The top bumps, the lowest that they go is 1, and the highest that these ones go is -1. So when it says what is the range of the cosecant function, what do I not have? Anything between what and what number? -1 to 1, right? Parentheses. So what I'm going to say for my range is I'm going to say that I have everything from -infinity to -1 with a bracket, and then I have everything from 1 to infinity, right? But I don't have anything between -1 and 1. What if I ask for the domain? I think I did on the other page, but the domain is what? X can't be what numbers?
Can't be.
Pi, 2 pi, 0. So I'm going to say 0 plus pi k. Or you could just write pi k. X is not allowed to be pi k. Any integer multiple of pi. What's period? Where does it start repeating? 2 pi, just like the sine function, right? Whatever the period was for sine, that has to be the period for cosecant, because it's the reciprocal of it, right? All right, so how about secant? Do you guys want to try it on your own, or you want me to do this one too? The other class was like, please do it.
No, we got this. We're smart.
Can you graph cosine at least on your own?
Yeah.
Cosine starts at 1. It has a period of 2 pi, so it's going to end back up at 1 once we get to 2 pi. Where is its lowest point? -1, and it happens at what radian measure? Pi, exactly. Because if you think about your unit circle, where is cosine the smallest? Cosine is the smallest. Oops, I don't know why I just drew it there after I just said it. Is that pi? That's where sine is the smallest. Cosine is the smallest right there, right at pi. Cosine is -1 there. All right, what are some other values that we know? What about pi over 2? What's the cosine of pi over 2? No, pi over 4. Pi over 2 is going to be 0, and 3 pi over 2 is going to be 0. And it has to be that wave function, curvy. Oops. And then we continue over here. Okay, so secant is going to be the reciprocal of cosine. So if cosine was equal to 0, that's where we have a vertical asymptote. Okay, so that's the first thing we draw, vertical asymptotes. And it happens where cosine was crossing the x-axis. Then from there, it's super simple. You just bump away from the previous bumps. So if you have, I know, it's weird. If you have a bump that's going downwards, your new one is going to go, the U shape is going to go upwards. So do you guys see what we're getting? Think you can handle that on the test, doing pictures like that? I think you can. So that's going to be secant. So if you want to label, one thing that might be useful on the homework is to label like and say, okay, I have secant of x and I had cosine of x. It's not tomorrow, don't worry. All right. So it says, as in the last section, we knew that tangent was different than sine and cosine. The same is true for cotangent. Its graph is much different than cosecant and secant. Okay, so cotangent, its graph will actually be pretty similar to tangent, right? They're reciprocals of one another. Okay, so cotangent is cosine divided by sine. So it's not defined when our sine is equal to 0. So sine is equal to 0 at 0, pi, 2 pi, 3 pi, and so on. Every integer multiple of pi. So as I'm drawing out the cotangent function, I'm going to have vertical asymptotes at 0, pi, 2 pi, and so on. Okay, so if you remember tangent, if I need to flip back, I can show you. Tangent started at 0, 0. It was an odd function. Okay, so if I look back to tangent, you guys can see. See how tangent, its starting point was right here? Okay. The starting point for cotangent is not there. Because it has to be a vertical asymptote because the reciprocal of 0 is undefined, right? Yeah, it actually starts at pi over 2. Because if you think about it, if I have cotangent of pi over 2, it's cosine of pi over 2 divided by sine of pi over 2. Well, cosine of pi over 2 is 0. Sine of pi over 2 is 1, so we end up getting 0. Okay, that's why it's starting there. As will all the other little cubic functions. They'll start on those points. But it does not look like x cubed this time. Any guesses? What do we think it looks like? It is the opposite way. Good job. Yep, it's the opposite way. It's like negative x cubed. And the reason, the key to doing cotangent and tangent, the ones I always think of, I don't think of any of the other ones. I think of my pi over 4s. At pi over 4, what is cotangent? Cotangent of pi over 4 is, this is not a hard question. Cotangent of pi over 4 is root 2 over 2 divided by root 2 over 2, which is 1, right? What's cotangent of 3 pi over 4? Negative 1, right? So do you guys see how it has to go downwards? It looks like a little panda bear, is that what you guys are saying? It has to go like that. It's the same thing here. It's just reversed, exactly. So you don't have to get your 1s and negative 1s in exactly the same place every single time. It's hard to draw. Oh man, I lost all of them. Let's do that. I know, don't you wish you could do Control Z on your homework sometimes? I've still missed it. We'll go with it. So it looks like that. Okay, so what's the domain of the cotangent function? We can have everything except for what values? Yeah, pi k, exactly. What is the range? All real numbers. What is the period? Where does it repeat? Pi. Yep. All right, let's put it all together in some graphs. We have 3 graphs here. Okay, this is what you guys are going to do. Want me to go back, Jordan? All right, this is what we're going to have on your homework. You're going to have 5 graphs total for your homework. That's it. Just 5 graphs. But I want you to draw all the steps, and I want you to talk about the transformations and all that. I want you to be very careful and use colored pencils, probably. Okay, or highlighters, whatever color you have. Okay, so here's exactly how I would do this on your homework. So for h of x, I have is equal to negative 2 cosecant of x. So what's that negative 2 doing? It's actually 2 transformations. Yeah, we have a vertical stretch by 2 and What's the negative do? Reflection over the x-axis. So if you have to draw cosecant, we need to draw its reciprocal first. That's what's annoying about these. Whenever you have cosecant and secant, you have to draw the reciprocal first, because how do you know where the asymptotes are and so on. Okay? So if I have sine, can you guys quickly do sine? It starts at 0, it goes up, it comes down. And you can label. So it ends at 2 pi, the middle's at pi, and so on. So what I would probably do is if I was doing this in a color, I would say, okay, this is sine of x. Grand. All right, so next up I have cosecant. So cosecant, do you guys remember how we used sine to get cosecant? You guys will be pros at this. You actually will like drawing cosecant because it's really easy. So you just do your dotted lines wherever it's crossing 0. And then we do the bumps away from the other bumps, right? So go away, 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 away. All right, and then our last thing, and you could break this into 2 transformations if you want to, is that we need that -2. So -2 cosecant of x. So it's going to flip it over, but what else is it going to do? It's going to stretch it, right? So we're going to have a skinnier U shape, and it's going to be going the opposite direction. So this one that we had right here is going to flip over the axis. It's still going to, its highest point is going to be 1 still, or -1, I guess. And then we just stretch it out. So do you guys see what's happening to all of these? Still at 1. Okay, so it looks like that. So if you want to do all your original ones in pencil and then your final one in highlighter or something, that would be useful. All right, let's do number 3 first before we do number 2. Number 2 is kind of the hardest. Okay, so number 3, so -4 cotangent of x plus pi over 2. There are 3 transformations. What are they? What about the pi over 2? Left pi over 2, that's called the phase shift, right? What about the 4? Vertical stretch by 4, that's called the amplitude. And then the negative? Exactly, so we have 3 transformations that occur. Now cotangent, we don't have to draw anything before we draw cotangent. That's the nice thing about cotangent and tangent. But do you guys remember where cotangent starts? Where's it undefined? I guess that's the key. Where are my vertical asymptotes? Yeah, 0, pi, 2 pi, and so on. So I'm going to have 0, pi, 2 pi, negative pi, negative 2 pi. But I'm going to the left pi over 4, or pi over 2. I shouldn't have drawn on all these dotted lines. So I'm really going to be, let's draw it over here. I'm really going to be at negative pi over 2, negative 3 pi over 2, pi over 2. Do you guys see what I'm saying? And 3 pi over 2. Now, cotangent usually went down like this, right? This is what cotangent looks like usually. So what's different? We already did the last thing. What about our vertical stretch by 4? So we're going to make it skinnier. It's hard to draw a vertical stretch when you have like the cubic shapes, but we're going to stretch it out a little bit. But it's also going to reflect over the x-axis. So what happens? It does. It looks like tangent. It's really the same as 4 times tangent of x, the new graph that we have. Oops. What is the what? That moved us left pi over 2. It moved all of our asymptotes, our starting positions. Do you see that? So that's our graph. So this is k of x here. This is our final answer. Yeah. All right, secant x. Okay, give yourself some room vertically for this one. Like I ran out of room originally, so we're gonna draw our axis like this because we're gonna have an up to, right? So what are our transformations? So we have up to, but we also have a vertical. Yep. So vertical stretch by 3, and then up to. All right, and we always kind of think about if we have a secant, we have to draw in cosine first. So cosine starts at 1, and it goes down and it goes up. All right, so this is cosine. So secant, we're going to take wherever it was crossing the x-axis. I should really label, but that's okay. And we go the opposite direction. Okay, that's secant. So our last step, we can do these 2 steps together, is that we're going to have 3 times secant, so it's going to get skinnier, and then plus 2. So we're going to go up 2. So a lot of times it helps to think about where your middle line is. Like originally your middle line's on the x-axis. Do you guys see that? But now this middle line is going to be up 2. So if you need to kind of draw a little middle line, that helps, and then go 1 unit up and 1 unit down from that line. So if we have 3 secant of x plus 2, we're going to have the same bumps, like the bumps go in the same direction, but they're just going to be skinnier. Like this one would be, its height of 1 is the highest point for the downwards ones. Do you guys see it? Kind of hard to draw. Okay, so you get that. Okay, do you guys understand this? A lot of things going on. The x-axis? Yeah. Oh, what were the original? So with cosine, we had 2 pi was at the end. Pi was the bump in the middle. So it's going to be pi over 2 and 3 pi over 2 for our asymptotes. So we write this on you can. All right, that's it.